Welcome to Quant Art, the YouTube channel which will introduce you to the art of quantitative finance. And in today's very first video, we will learn about random walk by solving the drunkman problem. Random walk is a fundamental concept in quantitative finance from which we derive the Brownian motion, which is at the core of all of our quantitative models. The drunkman problem is not only an application of random walk, it is also and mostly a very common interview question, and I had been asked this problem during a super day. So let's try to break it down and let's solve it. In the drunkman problem, you have a man that is coming from the bar to his home, but he is so drunk that he is not walking straight. So sometimes he goes forward as expected, but other times he goes backward. And the question is, how many steps on average does he need before reaching either the bar or home? Let's look at a graph. In this animation, the drunk man started at point 0. The bar is located at -10 and his home is located at 10. I use the probability of going forward equal to the probability of going backward, which has to be 0.5. If we go quicker, we can see that it's going back and forth, but we really need a 2D plot to have a clear understanding of the path that he is currently taking. In this plot, we have the x-axis which represents the number of steps and the y-axis which represents his location. So again, he started at 0, the bar is -10 and home is 10. We can see that he's going forward at the first step and then backward and then forward. And after 50 steps, he's almost reaching home, but not really. So how many steps on average does he need to either go back to the bar or go home? Let's now formalize the problem. Let's say that the drunk man is located at time 0 at step 0. So here in our example, the bar is at -3 and home is at 1, 2, 3, 4, 5. Every steps he makes, there is a probability that he goes forward and a probability that he goes backward. So for a step at time k, we have this xk random variable, which is either equal to 1 with probability p or -1 with probability 1 minus p. Very important, all the variable xk are IID, so independent and identically distributed. Let's define Sn, the position of the drunk man. So at time 0, as we can see here, is located at 0, and at time n is located at the sum of all the variable x, k from k equal 1 to n. Sn is a random walk. More precisely, since xk can either be 1 or -1, Sn in this case is a simple random walk. If p is equal to 1 minus p, in that case we have a symmetric random walk. In this video, we will focus on the particular case of a symmetric random walk because I believe it is a little bit more fun and elegant because we can use the properties of the martingales. For a more generic solution, we can use Markov chains with two absorbing states. Let's now define the concept of martingales. A martingale is a stochastic process, that is to say a sequence of random variable for which the conditional expectation of the next value, here mn plus 1. So knowing everything which happened in the past, so mn up until m1 or m0, it depends, is equal to the present value. From now on, I will note this conditional expectation E of mn plus 1 knowing n. We will prove that Sn and Sn squared minus n are martingales. Then we will be able to use the optional stopping theorem, which states that the expected value of a martingale at a stopping time, here capital N, is equal to the expected value of this martingale at its initial state, here m0. A stopping time is a random variable, usually n, which represents the time when we stop a process. Here, in our case, our drunkman is stopping to walk. The process ends when he is either reaching the bar or reaching home. And this is very important for our problem because we want to know when we stop walking. We want to know how many steps on average does he need before reaching the bar or reaching home. In other words, in this problem, we are interested in the expected value of the stopping time n. Now it's time to solve the drunkman problem. And as I mentioned earlier, the first step is to prove that Sn and Sn squared minus n are martingales. So, in order to prove that Sn, the symmetric random walk, is a martingale, we need to show that the conditional expectation of Sn plus 1 knowing n is equal to Sn. So, this is equal to the conditional expectation of Sn plus xn plus 1 by linearity of the expectation. We know that this is equal to the sum of the expectation. Thus, this is equal to Sn since we know n, and because the variable x or IID, this is equal to the expected value of xn plus 1, which is equal to 0 because it's a symmetric random walk, and p is equal to 1 minus p, which is equal to 1 over 2. Similarly, I will let you prove that E of Sn squared plus 1 minus n plus 1 is equal to Sn squared minus n. If you have any question regarding proving this equation, please let me know in the comments. Now that we know that Sn and Sn squared minus n are martingales, we can simply apply the optional stopping theorem, which states that the expected value of S at the stopping time n is equal to the expected value of S0, which is 0, and the expected value of Sn squared minus n is equal to the expected value of S0 squared minus 0, which is also equal to 0 because S0 equals 0. And now, in order to solve the drunkman problem, we simply need to solve these two equations. Let's solve the first equation. the expected value of S at the stopping time 10 is the expected value of being either at the bar or at home. Because if we are at the stopping time n, it means that we stopped walking, so we are either at the bar or at home. And this is equal to the probability of being at the bar with its value, so the location of the bar, which is -3, plus the probability of being at home multiplied by its value, its location, which is 5. Or, if you are at the bar, you can't be at home, because you are stopping to travel when you're either reaching the bar or home. And if you are at home, you can be at the bar. Thus, we have P of reaching the bar, probability of reaching the bar, is equal to 1 minus P of H, which is probability of reaching home. And thanks to the first equation, this is equal to 0. As a reminder, the bar is at -3 and home at 5. Now let's focus on the second equation, where E of Sn squared minus capital N is equal to the expected value of Sn squared minus the expected value of the stopping time n, which is equal to the probability of reaching the bar multiplied by its value squared, plus the probability of reaching home, which is equal to 1 minus the probability of reaching the bar multiplied by its value squared, minus the expected value of capital N. And we know from the previous equation the probability of reaching the bar, the probability of reaching home, and we know that this is equal to 0. Thus, we can easily compute the expected value of capital N. Here, we used a bar located at -3 and home at 5, but you can use any variables and you can solve the drunkman problem when we have a symmetric random walk. So we just solved the drunkman problem. We can now answer how many steps on average does this drunk man needs before going back to the bar or going home. But how does that help us? We want to learn about quantitative finance. That doesn't seem so related, to look at this movement of this drunk man going back and forth. Yes, we learned about interesting topics like random walk or martingales or stopping times, but how is it helpful to understand quantitative finance? If you look closely and with a lot of imagination, you might recognize the movement of a stock price. This drunk man might move a little bit like a stock. And this is fundamental, because random walk will lead us to Brownian motion, which will lead us to geometric Brownian motion, and then Black-Scholes formula, which is actually being used on the trading floor right now. So please subscribe, like the video, stay tuned, because in the next video we will learn about Brownian motion. I'll see you next time.